Something happened at CERN. Scientists still can't explain it. There is a machine hidden beneath Europe that most people will never see. It sits roughly 100 meters underground, running silently beneath farms, villages, and highways, crossing the border between France and Switzerland without ceremony. Above ground, the landscape looks completely ordinary. Cows graze. Traffic moves through roundabouts. The Alps rise in the distance. But deep below, in a circular tunnel stretching nearly 27 kilometers in circumference, something extraordinary happens every single second. This is CERN, the European Organization for Nuclear Research, and the machine buried beneath it is called the Large Hadron Collider. It is the largest and most energetically powerful scientific instrument ever constructed by human hands. Thousands of physicists from over 100 countries work with its data, and what it does at its core sounds almost too strange to describe. It takes the tiniest known fragments of matter and smashes them together at velocities approaching the speed of light, then studies the wreckage for clues about the deepest nature of reality. To appreciate why this matters, you need to think about scale. The particles being accelerated inside this machine are protons, building blocks found inside atomic nuclei. A single atom is already inconceivably small. You could line up tens of millions of them across the width of a human hair. A proton is smaller still, buried inside an atom the way a marble might be buried inside a sports stadium. And yet these invisible specks are what CERN works with. Not grains of sand, not dust particles, fragments of existence that no human eye could ever perceive directly. Two beams of protons travel around the ring simultaneously, one moving clockwise and the other counterclockwise. For most of their journey, they are kept carefully separated, but at specific locations along the tunnel, the beams are directed into one another head-on, proton against proton, matter against matter, two streams of almost unimaginable velocity meeting in a deliberately engineered catastrophe. The resulting collisions are catastrophically energetic events compressed into a space smaller than an atomic nucleus, lasting for intervals of time so brief they make a trillionth of a second seem leisurely. In those moments, familiar matter is effectively unmade and remade. Particles that do not normally exist in our calm, cool universe burst into being, fly outward in all directions, and vanish almost before they arrive. The tunnel itself is kept at temperatures lower than outer space, close to absolute zero, the theoretical minimum of all thermal energy. This extreme cold is necessary because the thousands of electromagnets lining the tunnel walls need to operate in a superconducting state, meaning electrical current flows through them with virtually no resistance. Those magnets bend the proton beams into their circular path and keep them focused into tight streams. Without superconductivity, the magnets could not generate fields powerful enough to hold particles moving at those speeds. So deep underground, a ring colder than the space between stars contains flashes of energy hotter than almost anything in the present-day universe. At the collision points, enormous detector systems have been assembled, machines within a machine. These detectors are layered structures, sometimes as tall as a multi-story building, wrapped concentrically around the point where particles meet. They cannot photograph something that lasts a trillionth of a second. Instead, they capture the traces left when particles pass through them. When a particle moves through a detector layer, it deposits a tiny amount of energy or leaves an electrical signal. That signal becomes a data point. Collect millions of data points from a single collision, and scientists can reconstruct what happened. What particles were created, where they went, how fast they moved, how much energy they carried. The particle itself is gone, but its shadow remains in the data. The detector systems at CERN record millions of collision events every second. The volume of raw data they produce is so large that no existing storage system could hold all of it. So the detectors are equipped with extremely fast automated decision systems that analyze each collision in a fraction of a second and discard routine events. Only unusual collisions, events where particles behaved unexpectedly or rare processes occurred, are flagged for permanent storage. This filtering happens automatically, continuously, relentlessly. What scientists are ultimately searching for in all of this wreckage is very specific, evidence of something the current rulebook of physics cannot explain. For roughly 50 years, the dominant framework describing the subatomic world has been called the Standard Model of Particle Physics. It is, by almost any measure, the most rigorously tested scientific theory ever developed. Physicists have subjected it to experimental scrutiny across decades, across continents, across generations of accelerators of increasing power and precision. Again and again, it has survived. Its predictions have proven accurate to an extraordinary number of decimal places, a level of precision that has no real equivalent outside fundamental physics. The Standard Model traces the enormous complexity of the visible universe back to a surprisingly small set of fundamental ingredients. There are quarks, the constituents locked inside protons and neutrons. There are leptons, which include the familiar electron along with its heavier cousins, the muon and the tau, and three varieties of nearly massless particles called neutrinos. There are force-carrying bosons, the photon for electromagnetism, gluons for the strong nuclear force, the W and Z bosons for the weak nuclear force. And there is the Higgs boson, the final confirmed piece of the puzzle found at CERN in 2012 after decades of searching. What makes the Standard Model so powerful is that it describes not just what exists, but what everything does. It predicts the rates at which unstable particles decay. It specifies the probabilities of different interaction outcomes. It even predicts the angles at which decay products should emerge from a collision. And it does all of this with staggering precision. Testing the Standard Model is like watching an archer claim to hit a bullseye from a kilometer away, and then watching them do it thousands of times without error. The theory's power extends to prediction. On multiple occasions, physicists calculated that a particular particle should exist before any experiment had ever seen one. The W and Z bosons were predicted and then found. The top quark was predicted and then found. The Higgs boson, which required the full power of the Large Hadron Collider to reach, was found exactly where mathematics said it would be. The theory told experimenters where to look, and the universe obliged every time. This history of success is precisely what makes the Standard Model both triumphant and frustrating. Because despite its extraordinary accuracy, physicists know with certainty that it cannot be the final word. The incompleteness is not subtle. It shows up in the biggest questions science asks about the universe. Gravity is the most obvious missing piece. The Standard Model describes 3 of the 4 fundamental forces with extraordinary precision. But gravity, the most obvious force in everyday life, the one that shapes planets, galaxies, and the fate of the cosmos, simply does not fit inside the theory. Including gravity in a unified quantum framework remains one of the most consequential unsolved problems in all of physics. Then there is dark matter. Astronomers studying the motion of galaxies have concluded that visible matter, everything made of atoms, accounts for only a fraction of the total matter in the universe. Something that exerts gravitational pull but does not emit or absorb light makes up the remainder. The Standard Model contains no viable candidate for this dark matter. Whatever it is, it lies entirely outside the known particle catalog. And perhaps most philosophically troubling is the matter-antimatter asymmetry. When particles are created in high-energy events, they tend to be produced in pairs, one particle and one antiparticle. When they meet, they annihilate completely, converting to energy. The Standard Model predicts that the Big Bang should have produced nearly equal amounts of both. If that were strictly true, they would have destroyed each other almost completely, leaving a universe of pure radiation and essentially nothing else. No stars, no planets, no us. Yet here we are. Matter exists in enormous quantities. Antimatter is almost nowhere to be found in the natural universe. Something in the early cosmos created a slight imbalance, just enough that when the mutual annihilation was complete, a thin residue of matter remained. That residue became everything that exists. The Standard Model contains some built-in differences between matter and antimatter behavior, but far too little to explain what we observe. Something else tipped the scales, and we do not know what. These gaps tell physicists that the Standard Model is an incomplete description of reality. A deeper theory must exist somewhere beyond it. Finding the edge of the known theory, the first place where its predictions fail, is one of the primary reasons the Large Hadron Collider was built. To understand how CERN looks for that edge, it helps to understand something about the early universe that the collider is uniquely equipped to briefly recreate. Rewind time far enough, and the cosmos looks nothing like today. In the first fractions of a second after the Big Bang, temperatures were so extreme that the particles and forces we recognize had not yet settled into familiar identities. The universe was a seething, undifferentiated ocean of energy and protomatter. Even protons and neutrons had not yet condensed into stable forms. Their constituent quarks and the gluons that bind them moved in a free fluid state, not locked into permanent structures but flowing together before cooling allowed them to solidify. This state is called quark-gluon plasma. Under ordinary conditions, quarks are permanently confined inside larger particles. No experiment has ever isolated a free quark. The forces binding them together grow stronger as you try to pull them apart. But in the quark-gluon plasma of the early universe, the temperature was high enough to temporarily overcome that confinement. CERN can recreate brief echoes of this state. Rather than colliding simple protons, scientists sometimes accelerate heavy atomic nuclei, typically lead nuclei, and bring them into collision. The energy released is sufficient to temporarily melt the interiors of the nuclei, creating a droplet of quark-gluon plasma that exists for an incomprehensibly short time before cooling back into ordinary particles. What scientists found when they studied this droplet was surprising. They expected it to behave like a gas, particles moving independently, bouncing in all directions. Instead, it flows. It moves like a liquid, but with internal resistance so low it approaches theoretical limits. Physicists describe it as one of the most perfect liquids ever observed anywhere. This matters because the way this primordial matter flowed helped shape everything that came after. The formation of protons and neutrons, the first atoms, the first stars, and eventually, the world we inhabit. The collider is, in this sense, a time machine, not one that transports people, but one that rebuilds physical conditions from the past in a controlled environment and allows their properties to be measured directly. The deeper purpose is to test whether the rules operating today are sufficient to explain the journey from that early fire to the present structure of reality. If those rules have gaps, if there are forces or particles that existed in the early universe and left their mark on everything that followed, they should show up somewhere in CERN's data. There is a particular class of events that physicists watch with extraordinary care: the decay of unstable particles. Most matter in the stable universe persists indefinitely under ordinary conditions. But in the intense environment of a particle collider, heavier and less stable varieties of particles are regularly created. These particles cannot hold their form. They carry too much energy and almost immediately transform into lighter particles, a process called decay. Decay is not random chaos. The Standard Model predicts with great precision not only what a particle can decay into, but how often each possible decay channel is used, and what the geometry of the resulting particles should look like. When an unstable particle breaks apart, the fragments carry the memory of the forces that shape the event. The directions those fragments travel, the angles between them, the ratios of different outcomes, all carry information. They are fingerprints of the interaction. Some decays are common and well understood. Others are extraordinarily rare, happening perhaps once in a billion or 10 billion instances. These rare decays are scientifically precious precisely because of their rarity. In a common process, the signal of any unknown influence is buried under noise. In a rare process, the background is quiet, and even a small departure from expectation becomes visible. If an unknown particle or force exists and interacts with matter even slightly, these quiet channels are where its fingerprints are most likely to appear. This is the principle behind one of CERN's specialized detectors, the LHCb experiment. Unlike the large multi-purpose detectors ATLAS and CMS, LHCb is designed specifically to study particles containing beauty quarks, also called bottom quarks. These heavy, unstable particles decay through processes that are sensitive to subtle physics. Their rare decay channels are particularly useful for searching for effects beyond the standard model, because any unknown particle or force marginally interacting with matter could leave a detectable distortion in the pattern of these decays. Among the most intriguing of these rare decays is a category physicists have named penguin decays. The name comes from the shape of the Feynman diagrams used to represent these interactions. Mathematical drawings with a looping structure that someone once decided resembled a penguin in silhouette. The nickname stuck through decades of serious scientific literature, so physicists now discuss penguin decays in formal journal papers without any sense of irony. The underlying physics is serious even if the name is not. A particular penguin decay that has attracted sustained attention involves a particle called a B-meson, a particle containing a beauty quark, transforming into several lighter particles including a kaon, a pion, and a pair of muons. This process is extraordinarily uncommon. The standard model predicts not only that it should happen very rarely, but also what the detailed angular distribution of the resulting particles should look like. Those angles carry information about every force that participated in the process. If the standard model accounts for everything, the measured angles should match the theoretical prediction within the expected statistical uncertainty. They have not matched as cleanly as expected. Over a series of measurements spanning more than a decade, the LHCb experiment has found that certain angular parameters in this decay are displaced from their standard model predictions. The displacement is not enormous. It is a statistical lean, a stubborn tendency for the data to cluster slightly off to one side of where it should sit. The difference has appeared across multiple independent analyses, across different data sets, and across increasing levels of experimental precision. It refuses to disappear. In particle physics, the significance of a measurement is expressed in terms of sigma, a statistical unit describing how far a result has drifted from what would be expected if only known physics were at work. 1 or 2 sigma deviations are common. They arise regularly from ordinary statistical fluctuation. 3 sigma makes people look closer. 4 sigma causes genuine excitement. 5 sigma is the threshold officially required before scientists declare a discovery, a level chosen because it is extremely unlikely to arise by chance, even accounting for the large number of measurements being made simultaneously across different experiments. The anomaly in the B-meson angular decay has fluctuated around the 3 to 4 sigma range across various analyses. That is enough to be taken seriously. It is not enough to declare a discovery. and physicists remain appropriately cautious because the history of the field contains pointed cautionary tales. Around 2015, data from the Large Hadron Collider showed a hint of an unexpected signal involving pairs of photons at a specific energy. It appeared independently in both ATLAS and CMS detectors, which made it significantly harder to dismiss as a detector artifact. Theoretical papers proliferated. Physicists speculated about what new particle might be responsible. The community was genuinely excited for months. Then more data arrived. The signal disappeared entirely. It had been a statistical fluctuation, a rare clustering of ordinary events that happened to mimic something new. This episode illustrates exactly why the 5 sigma threshold exists. Run an experiment long enough and look at enough variables, and you will eventually find something surprising purely by chance. Scientific discipline requires waiting until a signal is robust enough to survive every reasonable attempt to explain it away with known physics. The B-meson anomaly is difficult partly because it sits in territory where alternative explanations are genuinely hard to calculate. The decays involve quarks bound by the strong force, and the strong force is notoriously challenging to compute precisely in these contexts. Specific contributions from charm quarks can influence the measured angular distributions in ways that are difficult to pin down theoretically. If those contributions turn out to be larger than current calculations suggest, they might explain the apparent anomaly entirely within the existing theory. This creates a situation where the two most likely explanations are both plausible and both interesting. Either something beyond the standard model is affecting the decay, or the standard model itself is doing something physicists have not yet correctly calculated. In the first case, finding and characterizing the new physics would be revolutionary. In the second case, working out the correct calculation would deepen the theoretical understanding of how the strong force operates in complex bound systems. Either outcome advances knowledge. The particular role of muons in these and related anomalies deserves attention. In the standard model, the electron and the muon are considered essentially equivalent particles, differing only in mass. The muon is roughly 200 times heavier. Everything else about them should be the same. They carry the same electrical charge. They interact with the same forces. Their participation in any given physical process should follow identical rules, scaled only by the mass difference. Physicists call this equivalence lepton universality. It is a foundational assumption built into the mathematical structure of the theory at a deep level. If the theory is correct, processes producing muon pairs and processes producing electron pairs should proceed at identical rates when the mass difference is properly accounted for. Any violation of this principle would not simply indicate a new particle. It would indicate that one of the fundamental symmetries of the standard model is broken. Several measurements at LHCb over recent years have suggested that this equivalence might not be perfect, that certain decays produce muon pairs at slightly different rates than equivalent decays produce electron pairs. If lepton universality is genuinely violated, there would need to be some new physical entity that selectively affects second-generation leptons like the muon without equally affecting the electron. This would require new physics in a very specific and constrained form, not just a new heavy particle, but a new type of interaction with carefully defined properties. Various theoretical frameworks have been proposed for what that entity might be. One candidate is a hypothetical particle called a Z-prime boson, a heavier version of the standard model's Z boson with different coupling properties that distinguish between lepton generations. Another class of possibilities involves particles called leptoquarks, which would create direct interactions between quarks and leptons that simply do not exist in the standard model. Either discovery would be among the most significant in decades. While measurements of rare decays have occupied much of the spotlight, CERN has simultaneously been pursuing other deep questions about the nature of the universe. One of the most fundamental involves the direct comparison of matter and antimatter. When CERN creates antihydrogen, the antimatter equivalent of a hydrogen atom, consisting of an antiproton paired with a positron, it does so at a dedicated facility where conditions are carefully controlled. Trapping antimatter presents obvious difficulties. Antimatter annihilates instantly upon contact with ordinary matter, meaning any container made of regular material would destroy it upon contact. The solution involves sophisticated magnetic traps that suspend charged antiparticles in a vacuum, holding them away from the container walls through precisely shaped magnetic fields. Within these traps, physicists have been able to study antihydrogen with increasing precision. One of the most basic tests asks a deceptively simple question: does antihydrogen fall downward under gravity? From first principles, the answer is not entirely obvious. Theoretical frameworks have suggested that gravity might treat antimatter differently, perhaps causing it to be gravitationally repelled by ordinary matter, which would have dramatic cosmological implications. Recent experiments at CERN answered this question directly. When antihydrogen atoms were released from magnetic confinement inside a specially designed apparatus, their subsequent motion was tracked. The results showed clearly that antihydrogen falls downward, just as ordinary hydrogen does. Antimatter is not gravitationally special. It falls like everything else. This result closes off one speculative possibility for explaining the matter-antimatter asymmetry. Antimatter is not repelled by gravity. The mystery of why matter survived while antimatter nearly vanished remains open, but it is better constrained. This is how science often advances, not only by finding new answers, but by eliminating wrong possibilities and tightening the focus of the question that remains. The Standard Model was built on a foundation of symmetries, mathematical relationships between physical quantities that remain constant under certain transformations. One of the most important is called CP symmetry, which combines a transformation of charge with a spatial reflection. If CP symmetry were perfect, every particle process and its antimatter mirror version would be completely equivalent. Physicists have known since the 1960s that CP symmetry is not perfect. The Standard Model incorporates this CP violation through specific mathematical parameters, but the amount of asymmetry the theory allows is far too small to account for the observed predominance of matter. There must be additional sources of CP violation that have not yet been discovered. Finding them is one of the primary goals of the experimental program at CERN, and every comparison between a particle and its antiparticle is a search for that missing asymmetry. The matter-antimatter asymmetry is not a peripheral puzzle. It is the reason anything exists at all. In the first fraction of a second after the Big Bang, a tiny excess of matter over antimatter, perhaps one extra matter particle for every billion pairs, survived the great mutual annihilation that followed. That tiny residue is the entire material universe. Every star, every galaxy, every planet, every living cell is built from the overflow of a cosmic imbalance that the Standard Model cannot fully explain. Beyond all of these specific measurements, there is a broader question about what kind of discovery actually waits beyond the known theory. New physics, when it exists, often manifests first as a collection of small, nagging inconsistencies, measurements that persistently fail to match predictions by amounts just large enough to be worrying, but just small enough to be deniable. The anomalies at CERN have exactly that character. None of them individually constitute a confirmed discovery. Together, they form a pattern that is difficult to dismiss entirely. If an unknown particle is too massive for the Large Hadron Collider to produce directly, it can still leave fingerprints. Any new particle couples to known particles in some way. Even if it cannot be produced in a collision, its virtual influence, the quantum mechanical effect it has on processes that do occur, can shift rates and distributions by small but measurable amounts. This is the mechanism that makes rare decays so powerful as search tools. Any distortion in a known decay pattern points beyond the known physics. This approach has strong historical precedence. Before the top quark was discovered directly, its existence was inferred from its virtual influence on other measured quantities. Before the W and Z bosons were observed directly, their effects had been seen in other experiments. The theory predicted them, and their presence was felt before they were actually produced. Something analogous might be happening now. The unknown particle, a Z-prime boson, a leptoquark, something not yet imagined, might be too heavy to appear in current collisions. But it might be tugging on the decays of beauty mesons, shifting the angular distributions by the amounts observed. An unseen object announcing itself through the wobble of something visible. Or it might not. The calculations might improve. The anomalies might dissolve into known physics better understood. The history of the field contains many candidates for this fate. There is something philosophically important about how particle physics operates that deserves acknowledgement. The enterprise depends on an absolute commitment to what the data actually says, regardless of what scientists hope it will say. The hard-won culture of skepticism built into the field, the 5 sigma threshold for discovery, the peer review of analysis methods, the requirement that results be confirmed by independent experimental teams, is not a failure of imagination. It is the mechanism by which science avoids fooling itself. It ensures that when a claim does reach the threshold for acceptance, it has genuinely earned it. The anomalies at CERN sit below that threshold. They are genuine, persistent, and scientifically important, but they have not crossed the line into confirmed discovery. That could change with the next round of data from an upgraded LHCb or from improved theoretical calculations that clarify whether the standard model itself is responsible. Either outcome teaches something important. What seems certain is that the standard model is pointing beyond itself. The unanswered questions are too large and too fundamental to be explained by refinements within the existing framework. Dark matter exists and remains unidentified. The matter-antimatter asymmetry is unexplained. Gravity stands outside the quantum description of the other forces. Somewhere, a deeper theory exists. The question is where the first confirmed crack in the known structure actually appears, and whether we are currently watching its earliest visible sign. The Large Hadron Collider at CERN is one of the few instruments humanity has ever built that can approach these questions directly. Beneath farms and villages in the distant Alps, in tunnels colder than interstellar space, particles circle a 27-kilometer ring. Billions of times each second, proton beams meet in flashes of energy too brief and too small for any ordinary sense to register. From the debris of those meetings, scientists slowly read a message written in the language of physics at its most fundamental level. Most of what the data reports is confirmation. The rules hold. The standard model survives another test. But in some corner of the measurement, in the angular distribution of a rare decay, in the comparison between a muon and its lighter counterpart, in the rate at which a beauty meson falls apart in a detector deep underground, something keeps not quite matching. The deviation is small. It is persistent. It may be the first word of a sentence that changes everything thought to be settled about the universe, or it may eventually resolve into known physics better understood. Only continued investigation can distinguish between those two possibilities. The machine keeps running, the collisions keep happening, the detectors keep recording. Every hour, billions of events are cataloged, sifted, analyzed, and compared against the predictions of the most successful theory in the history of science. Somewhere in that enormous stream of data, there may be the answer to questions that have sat unresolved for 50 years. Why the universe chose matter over antimatter. what dark matter actually is, whether there are forces and particles that have remained hidden through every previous experiment, and whether the extraordinary theory that has guided physics for half a century is truly the final word on what reality is made of, or merely the most successful chapter so far in a story that is far from finished. The Standard Model is a cathedral built from 5 decades of measurement and mathematics. Its arches hold, its walls are strong, but somewhere behind the sealed doors, something waits. The building itself tells you that much, through galaxies that spin too fast to be held by visible matter alone, through the empty space where antimatter should have been, through the slight and stubborn misalignment of a particle falling apart in a tunnel 100 meters underground. The universe has not finished speaking, and beneath France and Switzerland, in the darkness and the cold and the light of particle collisions, human beings are still listening for what it has left to say.